Ladies and gentlemen, you are welcome to my YouTube channel. In today's class or in today's video, we are going to look at the concept of quantum numbers. So what is quantum numbers? Generally, quantum numbers are the numerical values that try to describe the unique quantum state of an electron in an atom. So you know that actually we arrange electrons in an atom using either orbital configuration or using a shell configuration. So in one atom, you can have 20 electrons, 5 electrons, 10 electrons. So assuming now you are actually interested in one specific electron in a particular atom. So to actually have the understanding of the unique states, the unique quantum state of that electrons, you need the knowledge of quantum numbers. So these quantum numbers, they arise from the solutions to Schrödinger equation in quantum mechanisms. So understanding quantum numbers is essential for grasping atomic structure and the behavior. So if you have a good understanding of the quantum number, it will give you an idea of how the atomic structure look like and the behavior of the atom. So what are those four quantum numbers? Of course, these four quantum numbers, we have them as principal quantum numbers as number 1, and we have azimuthal quantum numbers, we have magnetic quantum numbers, and we have spin quantum numbers. And each of these quantum numbers have their unique characteristics and feature in a particular electron. So the principal quantum numbers is represented with small letter n. Then the azimuthal quantum number is represented with small letter l, while the magnetic quantum number is represented with small letter m, subscript l, and then the spin quantum number is represented with small letter m with subscript s. So these are the four quantum numbers that we have in chemistry. So now, what are quantum numbers? So quantum numbers, what they do, they actually provide information about the size, the shape, and the orientation of atomic orbitals. So these are the full information that we usually trapped from the quantum numbers. They give the size, the shape, and the orientation of atomic orbitals. And they are used to specify the energy levels of an electron in an atom. So if you have a particular atom and you want to know the energy level of that particular electron in an atom, then you use quantum numbers. So each electron in an atom is described by a unique set of quantum numbers. You can have 10 electrons in an atom. You can have 11 electrons like in the case of sodium. But each of that electron in an atom have their own unique set of quantum numbers. So therefore, no two electrons in an atom have the same four set of all the quantum numbers. In fact, this is a theory and we are coming to that. So then, what are the types of these four quantum numbers? What are the types of quantum numbers? So we have four main types of quantum numbers. So these quantum numbers, we have principal quantum number, we have angular or azimuthal quantum number. So angular quantum number and azimuthal quantum number is the same. Then we have magnetic quantum number, and then we have spin quantum number. So each type serves a different purpose in describing electron behavior. So each of these types of quantum numbers have their own behavior. Like for example, now let's look at the principal quantum number. So what the principal quantum numbers is, it actually describes the distance of electron from the nucleus. It actually shows the position or the distance of electron from the nucleus. Like for example, this rate here indicates the nucleus, and of course this is an electrons. This is an electrons on the shell. So if you ask to describe or to identify what is the principal quantum numbers of these electrons highlighted in red, of course, the first shell is is 1 because as we said, n represents the principal quantum number. So if n is 1, it means that there is 1 shell. So if n is 2, it means that we have 2 shell. And if n is 3, it means that there is a 3 shell. So the electrons that I highlighted here in red is in shell 3. So that is why the principal quantum number here is 3. That is, the n is 3. So that describes the distance of electrons from the nucleus is at shell 3. The electrons is at shell 3. So that is what the principal quantum number does. So it actually gives an idea of how the electrons distance itself from the nucleus to the outermost electron, or to the electrons itself. Then the next one is, of course, the azimuthal quantum number. So what azimuthal quantum numbers it gives, actually give the shape of an orbital. It gives the shape of an orbital. So each orbital have its own shape, like S orbital have a spherical shape, P orbital have a dumbbell shape. So this is actually how the azimuthal quantum number does. It actually gives the shape of an orbital. And then the next one is the magnetic quantum numbers, which actually give the orientation of the orbital. And then, of course, the spin quantum numbers, it gives the orientation of the electron. Some electrons are clockwise, some electrons are anti-clockwise. So it gives the direction as well as the orientation of an electron spin. So together, these quantum numbers, they define the position and energy of electrons in an atom. So we are going to look at them one after the other, starting with the principal quantum number. So the principal quantum number, which is actually represented with 1 letter n, it indicates the main energy level of an electron. And it can be actually, it can take a positive integer values. So you can never see it as negative. So, of course, the principal quantum numbers integers, it can be 1, 2, 3. So if it is 2, it means that there are 2 shells. If it is 3, it means that there are 3. So the principal quantum number and energy level means the same thing. So if the principal quantum number is 3, it means that the energy level is 3. If the principal quantum number is 5, it means that the energy level is 5. So larger values of n correspond to higher energy levels and the greater distance from the nucleus. So the higher the values you have for the n, it means that the higher the energy level and the more the distance between the outermost electrons and the nucleus. So the principal quantum numbers actually, it's of course donates the probable distance of an electron from the nucleus. So then the next thing is angular momentum. So the angular momentum quantum number, which is also the same thing as the azimuthal quantum number. So the angular quantum number, it defines the shape of the orbital. It can take a values from 0 to n minus 1, where each value corresponds to a specific type of orbital. For examples, if you have L is equal to 0, then it means that it represents s orbital. So when L is 0, you have s orbital. Of course, this is it. So when L is 0, which is angular momentum, when it is 0, then you have s orbital. And the shape, as we described, that's the angular momentum gives the shape of an orbital. So it means here, since L is 0, so it is s orbital, and the shape of s is sphere or spherical. And then when L is equal to 1, L means p orbital. So it is dumbbell. And when L is equal to 2, then we have d orbital, which is a complex, or sometimes we call it double dumbbell. And then when L is 3, then it means it is f orbital. So you should know that whenever you see L is 0, so it means that you are dealing with s orbital, and whenever you see L is 2, then you are dealing with p orbital, and when it is 3, then you are dealing with f orbital, and the shape of f orbital is more complex, and sometimes we call it multiple loops. So you see, each value of L represent a particular orbitals, and each of the orbitals have their own specific shape. So this is dumbbell shape, this is double dumbbell, and this is a multiple loops, and this is sphere or spherical. So that is actually for the angular momentum of the quantum number. Let's say now, for example, in sodium, the atomic number of sodium, because let's have it here. The atomic number of sodium is 11. So to know the electronic configuration of sodium, we are going to have one S2, 2 S2, then 2p, we have 2p6 here, and then we have 3 S1. So now if you ask, based on what we discussed, if you ask to describe the quantum number of the 11th electron. This is the 11th electron. So based on what we discussed, if you ask to describe the quantum numbers of the 11th electron, so it means that, look at the energy level here is 3. So it means that from here, you know that you have your n is equal to 3. And which shape is this? Since the 11 electron is on s orbital, so you know that when you have s orbital, it means that your L is equal to 0. So since this 11th electron is on s orbital, then it means that we have our L, L. We have our L is equal to 0. We see now, first, from what we have discussed, we were able to describe the two quantum numbers of the 11th electron in sodium. So this is how we will go about it seriously. So now, you see, for the 11th electron in sodium, it is on s orbital, so that is why the L value for the 11th electron is 0. And of course, if you see that the last energy level, or the energy levels of the 11th electron is 3, so that is why we have n equals to 3. So now the next thing is magnetic quantum number. So the magnetic quantum number, it specifies the orientation of the orbital in space. So it can take integer values ranging from minus to plus, including 0. Like, for example, now if we have, let's look at it here. If we have of course, let me just do it like this. So we know that if we have L is equal to 1, let's say we have L is equal to 1. But now the question is, what are the possible value of L when n equals to 2? So you see that we have n equals to 2. It means that we have how many energy level? We have 2. Let's say when we have n is equal to 2, that is when our energy level is equal to 2. So we can see clearly we have 2 possible values of L. So why do we have these 2 possible values of L? Is because you know that when we are talking about the L, you know that we give a formula which says L is equal to n minus 1. So you see here, when we have L, so when n is equal to 2, so we can now say 2 minus 1, which is actually going to give us 1. And then you can also, at the same time, since you have also 1 here, so the L can also be 1 minus 1. So for the second shell, we can have 2 minus 1, which is actually going to give us 1. And then, of course, it means that in the atom, we have 2 shells. So for the first shell, we have L equals to 1. So I'm now going to have L equals to 1 minus 1. So this 1 minus 1 is going to give us 0. So that is why we have the value of L as 0 and 1. So we have 0 and 1. That is why we have these two values. That is why we have these two values here. So, but now the question is, of course, so when we have L is equal to 1, what will be the M value? So as we said, the value of M, which is the magnetic quantum number, is ranging from minus 1, 0, sorry, minus L. I wanted to say minus L, 0 plus L. So what does that mean? It means that when you have L is equal to 1, then it can be, the value of M can be minus 1, it can be 0, and it can be plus 1. Let me give another example. Let's say you have L is equal to 2. So if L is equal to 2, since you have the range of value to be minus L, 0 to plus L, so it's going to be, we are going to start with the minus 2. Then after minus 2, the next one is minus 1, then 0, then plus 1, and then the last one is plus 2. And if it is L, if L is equal to 3, then it is going to be minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. So you see, like, for example, now here, by looking at this one, we see that we have L equals to 0. So for the magnetic quantum number, it is 0. That is what I wanted us to understand here. And then when N is equal to 2, then the L is equal to 0 and 1. So for the magnetic quantum number, for the 0, it's going to be remain 0. And then for the 1, it's going to be minus 1, 0, and plus 1. And then for the N equals to 3, so you have three possible values of L, 0, 1, and 2. So for the 0 in the magnetic quantum number, it remains 0. And then for the L value as 1, is going to be minus 1, 0, and plus 1. And then for L equals to 2, then we have something like this. So this is how it goes. So it means that, what does that mean? So remember, I told you when we have, of course, L equals to 2, it means that we have d orbital. So since L is equal to 2 and we have d orbital, so what does that mean? Based on these values, we have 1, 2, 3, 4, 5. It means that d orbitals have 5 subshells. D orbital have 5 subshells, something like this. It has 5 subshells. So we have 1 here, 2, 3, 4, 5. So we have 1, 2, 3, 4, 5. So we have minus 2. So the first subshell have minus 2. The second subshell has minus 1. And then the third one have 0. And then the fourth one have plus 1. And the last one have plus 2. So this is how we are going to have it. Minus 2. This is the minus 1. This is the 0. This is the plus 1. And this is the plus 2. So these are the 5 subshell we have for the d orbital. And of course, for L equals to 1, of course, it is p orbital. It is p orbital. So that is why p orbitals have 3 subshell. P orbital have 3 subshell. Like this. So the first one here is -1, this one is 0, and this one is +1. So that is why the one with -1 is px, and then the second one is py. So this is py, and then the last one is pz. So these are the three subshell for p orbital. So that is how magnetic quantum number give it its own orientation of an atomic orbital in space. And of course, look for the when n is equal to 4. When n is equal to 4, then we have L equals to 3 here. So when L is equal to 3, it means that there are 1, 2, 3, 4, 5, 6, 7. It means that there are 7 subshell. There are 7 subshell. So this is how to know the number of subshell for each and every atomic orbital, for each and every atomic orbitals using magnetic quantum number. And of course, when n is equal to 4, you see the energy level, all the orbitals will have the same energy level, which is 444. Like for example, since n here is 1, so we have 1s. Since n here is 2, so we have 2s and 2p. Since n is 3 here, we have 3s, 3p, 3d. So this is how it behaves, and the number of orbitals in subshell, the number of orbitals in subshells are calculated like this. Like for example, with this one that we have n, sorry, we have the number of subshell as 7. In fact, we even have a formula for calculating the number of subshell, which is 2l plus 1. So you can use 2l plus 1, 2l plus 1 to give you exactly the number of subshell for each and every atomic orbital. Like for example here where we said 3 have 7 subshells. So how do we calculate it? So since our L here is 3, here this one is red. So what we are going to do, we are now going to say 2 into 3, then plus 1. So 2 times 3 is 6 plus 1, then it's going to give us 7. So we have 7 subshells. So this is actually a formula that you can use, calculate a subshell. So the next one is spin quantum number. So for the spin quantum numbers, it describes the intrinsic spin of an electron. So it can have one of two values. It can have +½ or -½, indicating the two possible spin states. It can have positive values and it can have negative value. So the spin quantum numbers is crucial for understanding the Pauli exclusive principle. So what Pauli exclusive principle states that no two electrons in an atom will have the same for all quantum numbers. So I'm coming to that. Like for example, now for the spin quantum numbers, we have ms. So this leads to, of course, this leads to the fourth quantum number. So the spin quantum numbers, which is ms, the spin quantum numbers has only two allowed values, +½ and -½. So if you have the electrons pointing upward in this direction, it means that it is the positive half. And when it is pointing downward, that is anti-clockwise like this, it is negative. So that is why it's not possible to have two electrons in an atom to have the same values for all the 4 quantum numbers. So let me just give example here. Let's say you want to know the 4 quantum numbers of let's say 6th electron in sodium. So that sodium have atomic number 11. So the first shell we have 1s2. The second shell we have 2s2. 2s2, then we have 2p6, and then we have 3s1. So where do we have our 6 electron? So you see, the best thing now to do is to draw the box. So you see the first box have 2 electron here. The second one also have 2 electron here. And then, so where are we going to have our 6 electron? So you see we have 1, 2, 3. We have 1 here already, 2. We have 3 here. And then we have 4. So this is the 5th electron. And then this is the 6th electron. And we are going to describe why here we put all the 2 electrons at once, and here we have to put them singly. So you see we have 1, 2, 3, 4 electrons here, and then here we have 5. So this is the 6th electron. So now, how do we get the quantum numbers of the 6th electron? This is of course our 6th electron here. This is our 6th electron here. So first, to get the value of n, what is going to be the value of n? So you see from the energy level here, you can clearly see that since it is here, so the n is equal to 2. That is the principal quantum number is 2. And then since it is p orbital, so remember, if the orbital is p, what is the value of l? It's 1. So we now have l is equal to 1. So you see we have n is equal to 2, then we have l equals to 1. So what will be the value of our magnetic quantum number? So remember, for the p orbitals, they have 3 values. We have -1, we have 0, then we have +1. So the first box have -1, the second box have 0, and the third one have +1. So you see our 6th electron is under which box? Under 0. So we have our Ml, which is the magnetic quantum number is 0. So then what next is the spin quantum number? So is the electron pointing upward or downward? It is pointing upward. So it means that our spin is going to be +12. It's going to be +12. So we now have +12. So these are the 4 quantum numbers of 6 electron in sodium. So this is how to describe the quantum numbers of an electron. So then what next? The Pauli exclusive principle. So the Pauli exclusive principle is a principle that states that, you should all know this. It's a principle that states that no 2 electrons in an atom can have the same set of the quantum numbers. So there is no way you can have an electron in an atom, in one atom, in a single atom, to have the same set values of all the 4 quantum numbers. At least they must have opposite spin. So this principle explains the arrangement of electrons in different orbitals. It helps in arranging electrons in different orbitals, and it is fundamental to the structure of the periodic table and chemical behavior. So now let's look at which one is correct here. You see, in the 2s, you have 1 electron pointing upward and 1 pointing downward. So you see here we said is correct. But look at the second one here. You can see that we said it is incorrect. Why is it that it is incorrect? Because both of the 2 electrons are pointing upward. They are pointing the same direction, which is not possible. It's not possible. You see, so the one pointing upward is +12, and the one pointing downward is minus. So that is why if you have 2 electrons moving in opposite direction, it means that the charges are nullifying one another by becoming neutral. But in this case, if you look at them, they are all pointing the same direction. Also in this one, they are all pointing downwards. So
incorrect to have this kind of arrangement. They must be in opposite direction within the same box. So then electron configuration and quantum numbers. So electron configuration describes the distribution of electrons among the various orbitals. So quantum numbers are used to write these configurations systematically. So understanding electron configuration helps predict chemical properties and the reactivity. So you see, this is the electron configuration. So writing electron configuration, you can write electron configuration using using SPDF notation or using a shell. So one thing that we should understand, each of every shell have the number of maximum electrons that it contains. Like S orbital accommodate a maximum of 2 electrons, P orbitals accommodate a maximum of 6 electrons, D shells or D orbitals accommodate a maximum of 10 electrons, while F shell or F orbitals accommodate a maximum of 14 electrons. This is how electrons are arranged. So now what next? You can also follow a rule or the Auber principle or Auber rule, which actually states that electrons are arranged from lower energy level to the higher energy level. So let's go down. We are coming to describe the concept of the Auber principle. So this is the Auber principle. So the Auber principle states that electrons occupy the lowest energy levels or the lowest energy orbital first. So you see here we have 1s, we have 2s, we have 2p, 3s, 2p, 4s. So it means that the electrons should be arranged in this direction. First, you have to start with 1s, then you also add your electrons in 2s, then 2p followed by 3s. This is the arrangement of 8s. Assuming now you have, let's see, you have calcium. Let's say you have calcium and the atomic number of calcium, of course, is 20. It's 20. So if you want to arrange these 20 electrons, how are you going to start? So you have to start it from this 1s. So we take 1s, and s, of course, accommodate a maximum of 2 electrons, and then second 2s. And after 2s, the next one is 2p. And we know that 2p accommodate a maximum of 6 electrons, so we pick 6 electrons. And then the next one is 3. We have 3s2. So after 3s2, then the next one is 3p. So we have 3p6. So after 3p6, the next one is 4s. So we have 4s2. So if you have this is how you are going to follow in arranging electrons. So you see, you start from the lowest energy level moving to the highest energy level. So since it is calcium, which is 20, so let's count the index number. So you have 2 plus 2, which is 4. So 4 plus 6 is 10. 10 plus 2 is 12. 12 plus 2, plus 6 is 18. 18 plus 2 is 20. So you see we have 20. So this is how we arrange electron using shell, starting from lower energy level to higher energy level. So the principle guides the order in which quantum numbers are assigned to electrons, and it is essential for determining the electronic configuration of an atom. So then the next rule, so you see here, we talk about Hund's rule, and then second, we talk about fully exclusive principles. Then we talk about our principles. So the next thing now is Hund's rules of maximum multiplicity. Hund's rules of maximum multiplicity. So the Hund's rule said that electrons will fill degenerate orbitals singly before pairing up. So generally, when we are arranging electrons in an orbital using a box, so the first thing we arrange the electrons in the degenerate orbital singly before pairing start taking place. And what are the degenerate orbitals? We need to understand the degenerate orbitals. Degenerate orbitals are the orbitals that split in the magnetic field. So what are those orbitals that split in the magnetic field? It's P, D, and F orbitals.
S orbital is not degenerate orbital because if you check in the magnetic quantum numbers, we have 0 value for the S orbital. So that is why it doesn't split. So now, according to these rules, how do we arrange these electrons singly before you start firing them? So the idea is actually like this. Look at this here. So we have two S. So S already is not a degenerate orbital. So you see here we put the two electrons here at once. And then here you put them singly. So you put them single here, you put them single here. You can't just put these two electrons 2p at the same time because they are degenerate orbitals. Let me just give example. Let's say you have your box like this. Let's say you have one S2 here. You have one S2, you have two S2, and then let's say you have two P6. So how do we follow these rules? Let me show it. Let me demonstrate it more here. So you see here we have 6 electrons and here we have two electrons. So because S is not degenerate orbital, you can just put the 2 electrons at the same time. Here you can also put the 2 electrons at the same time. So but what of in the case of this 3p? You can't just, you see here is 6, but you can't just put the 6 electron or the 2 electrons here at the same time. It's wrong with that. So you have to arrange it first singly before you start pairing it off. What did I mean? It's this. So you have to first, after you have this, then what you are going to do is, okay. So what you are going to do, you arrange singly. So you add 1 electron here, then add 1 here, then add 1 here. Then you start pairing singly, coming back here, coming back here, coming back here. So you see, you arrange them singly first, and then you come back and start pairing. So this is what Hund's rules of maximum reducibility state. So this rule minimizes electron repulsion and stabilizes the atom. So it is an important consideration when assigning quantum numbers to electrons. So when you are trying to assign a quantum numbers of an electron, it is very, very important to consider these Hund's rules. If not, you are going to make mistakes. So what are the summary of quantum numbers? So each electron is uniquely identified by a set of 4 quantum numbers. And these 4 numbers define energy levels, orbital shape, orientation, and spin state, and they are essential for understanding atomic structure and electron interactions. So ladies and gentlemen, we are going to stop here, and thank you very much, and I hope this video will be of help to you, and don't forget to join the YouTube community for you to have access to all our videos. Thank you very much for your time.